All right, here's your first video for chapter 16, which is all about acids and bases. I'm going to try and make more shorter videos so you don't have to sit for as long as some of my videos are. So this first video is going to be just covering Arrhenius theory, Bronsted-Lowry theory, and how to calculate pH, K, and pKa. Okay, so it sounds like there's a lot of topics, but it's really fairly straightforward. So acid-base theory has several different levels. The earlier theories were sufficient for a while until they found other scenarios where the rules didn't apply, so they had to come up with new things. So it's kind of progression through science. But the first one is a pretty solid rule, and it's called Arrhenius theory. Okay, recognize that name, Arrhenius. We dealt with the Arrhenius equation in previous chapter. But the Arrhenius theory is pretty straightforward, and it says that acids produce H+, and bases produce OH- in water. Okay. Anything that's an acid will make H+ in water. Anything that's a base will make OH- in water. So before we get, and I'm going to try and avoid a pitfall that happens every time I teach acid-base chapter. So whenever you have H+ in water, and to be clear, H2O. The H2O will immediately grab that H+. Okay, the H+ it's never just floating around as just hydrogen ions. Okay, we keep track of it so that we can talk about acid strength, but we never actually have H+ just floating around in water. So immediately the water picks up that hydrogen ion and makes H3O+. We call this hydronium ion. Okay? Because this is such a sort of automatic and assumed thing, as we go through this chapter and pretty much forevermore, H+ and H3O+ mean the same thing. Okay, we will often use H+ and H3O+ interchangeably in our terminology. Okay, so don't think about those as two separate things. Whenever we're talking about H3O+ concentration or H+ concentration, we're talking about the same thing. Okay, so in water, the Arrhenius theory says that acids produce H+ and bases produce OH-. Okay, and the way we talk about that is with the pH scale. Okay, so whenever we're talking about sort of how acidic or basic things are, we use pH, and you've probably heard that term before. You know, it's all over commercials, pH balanced for your skin's comfort and things like that. And what it is a description of acid strength. Okay, and in general, P is just a mathematical operation. Okay, anytime you see P in front of anything, that means take the negative log of that thing. Okay, in this case, it's pH. We're also going to talk about pKa. So that means take the negative log of Ka. Okay, so if we're talking about the pH, we're specifically talking about the negative log of the H+ concentration. Okay, and this, remember, anytime we see brackets, this is in molarity. All right, and then conversely, and this is the way we do this by convention, okay, because we could just as easily talk about the pOH of a solution, which just means the negative log of the OH minus in a solution. Okay? So there is a very handy sort of relationship between pH and POH, in that pH plus POH equals 14. Okay, which is really handy for us. Okay, so but by definition, by convention, the chemistry world has agreed, whoops, that's the wrong one. Sorry. By convention, we've agreed to use the pH scale instead of the POH scale. Okay, by convention, if you can't read my handwriting, it's a little bit messy. All right, so let's do a quick little example. All right, so find the pH of a solution that is 0.01 molar NaOH. Okay, so I can write an ionization equation for this. Right? And the ionization equation looks like this. We put some solid sodium hydroxide in water, and what it does is it ionizes to Na plus aqueous plus OH minus aqueous. Right? And because we have a 0.01 solution, that means that the concentration of OH minus is 0.01 molar. That should be a capital M. All right, and we sort of did this when we were the same idea when we were dealing with colligative properties. Remember when we were talking about concentrations of ions in a solution given the concentration of a compound, right? If I have 0.01 molar sodium hydroxide, that means that I have 0.01 molar sodium plus and 0.01 molar OH minus. Okay, so if I want to know the pH, I first have to find the POH. Okay, because that's all I have at the moment. So POH, we take the negative log of 0.010 equals 2. And then pH plus POH equals 14. So the pH equals 14 minus the POH. 14 minus 2 is 12. Okay, so there's a lot of, in this chapter, there's going to be a lot of relationships between pH, POH, H plus, OH minus. So we have a couple of equations that we're going to get into that will allow us to do that. This one is our first equation that gives us the relationship between pH and POH. Okay, so if you know one, then you can easily find the other. All right, so the Arrhenius theory is completely dependent on production of H plus and OH minus in water. Okay, but it doesn't work for all situations. All right, so let's look at a version of things where we don't get H3O plus or OH minus, but we're still dealing with an acid-base scenario. All right, so let's look at what we get when we have some hydrobromic acid. And it's actually hydrobromic acid gas, okay, with some methanol. All right, so we don't have any water in this situation. No water present. Right, we're dealing with some organic solvent, this methanol, right? And so what we get is a compound that looks like this, and some bromine ion. Okay, so this is still an acid-base reaction. Right, but we don't have any H plus or H3O plus produced. We don't have any OH minus produced. But by experimentation, we still know that this is an acid-base reaction, primarily because that's an acid. Right? It's called hydrobromic acid for a reason. Okay? So chemists had to come up with a broader definition. Enter our new theory, which is the Bronsted-Lowry definition. Okay? And the Bronsted-Lowry definition is that acids donate protons. Okay? Or they donate H plus. Right? Remember, hydrogen atom, normally a neutral hydrogen atom has a proton and an electron. If we take away the electron, all we're left with is the proton. So when we say proton, we're talking about H plus. Okay, just want to make sure that that's very clear. So, but acids donate protons and bases accept protons. Okay, so if we look back at our non-water acid-base reaction with hydrobromic acid, we've got HBr plus our CH3OH gives us CH3OH2 plus and some Br minus. Okay, so the easiest way to sort of look at this is start with one component and then find that component on the other side of the reaction. Okay, so let's start with the HBr. Right, what does the HBr become as a product? And the answer is that it becomes the Br minus. Okay, so looking at what happens to that HBr in the course of the reaction, it loses a proton, right? It goes from HBr to just Br minus. So the HBr donates a proton, which makes it the acid. Okay, aside from the fact that we call it hydrobromic acid, we can look at it in terms of the Bronsted-Lowry definition, that HBr donates an H+. Right? Now let's take a look at our other component, our CH3OH. We find it on the right side of the equation. And CH3OH becomes CH3OH2. Right? It now has one more proton than it did before, one more hydrogen. Right? So it accepted a proton. Right? And if it accepts the proton, that means that it's the base. All right? So what we have here are what we refer to as conjugate pairs. Not conjugate, sorry. Conjugate. There we go. Conjugate pairs. So the HBr becomes Br minus. So what we're going to do is we're going to label these, and let me use a third color yet. So the HBr is the acid, okay, and that's easy because it's called hydrobromic acid. And then we find that it donates a proton, and when it donates that, what it becomes, we call this the conjugate base. Okay, an acid becomes a conjugate base, and as you might guess, our CH3OH minus is the one that accepted a proton, which makes it a base. And what it becomes is called the conjugate acid. Okay, an acid becomes a conjugate base, and a base becomes a conjugate acid. And you will be required to identify acid-base, conjugate base in a reaction. Okay, that is a normal question in this type of chapter. Okay, so the important thing is that an acid becomes a conjugate base, and a base becomes a conjugate acid. Okay, so the easiest thing is to identify who's the acid and who's the base first. Which one donates a proton, which one accepts a proton. That will identify the acid and the base. And then what they become are the opposite conjugates. Okay, and actually I think I'm going to stop here with this particular video. We're going to continue on with the next video talking about relative acid and base strength.